Welcome to the first part of this webinar about new energy storage technologies. This talk is about thin-film solar cell materials analyzed by X-ray photoelectron spectroscopy. We will briefly look at the theory of how XPS works and what information it can give us, and then move on to some case studies of how it can be applied to analyze solar cell materials. X-ray photoelectron spectroscopy, or XPS, is a surface analysis technique. But what do we mean by the word surface? Without using ion milling, XPS can measure information between 0 and 10 nanometers into the surface, corresponding to the red and blue zones of a diagram on the slide. Most other techniques cannot analyze this very thin zone, and this surface sensitivity is one of the strengths of XPS. If we want to look deeper, to analyze buried interfaces, for example, we can combine XPS with ion milling, and then we can analyze samples up to the micron scale of thickness. For inorganic materials, we normally set a limit of 2 to 3 microns for depth profiling, although it's probably possible to go further on a modern instrument. With organic materials, we can easily go beyond 100 microns thickness with no issues. This slide shows a brief description of how XPS works. More information can be found at the website noted on the bottom of the slide, xpssimplified.com. An X-ray beam incident on a solid surface will cause photoelectrons to be emitted from the top 10 nanometers of that surface. The energy of the X-rays is typically 1.5 kiloelectron volts. The kinetic energy of the photoelectron tells the analyst 3 things: the element and the electron orbital from which the electron came, and perhaps more importantly, the chemical bonding state of that element. It is this ability to measure chemical state information that sets XPS apart from many other techniques. For example, if we were analyzing a copper surface, we could distinguish between copper metal, copper 1+, and copper 2+ oxidation states. We could also quantify the amount of each oxidation state present. This slide shows a thermoscientific Nexa surface analysis system and shows just some of the possible applications for XPS when looking at solar cell materials. X-ray photoelectron spectroscopy can help in a lot of analytical situations, especially where the problem is at the surface or at an interface between layers. Using XPS, it's possible to find problem locations on a surface, and depth profiling enables the analyst to probe into the bulk of a material. An important feature of XPS is the ability to quantify the concentration of elements or chemical states without using reference standards. XPS is also able to measure electronic information from solar cell materials, such as valence band offsets or work functions. Looking in some detail at how XPS can be useful for solar cell analysis, we begin with compositional depth profiling. XPS and ion milling are combined to gently but rapidly sputter through a solar cell device while also collecting XPS data. In the example shown on this slide, the solar cell device has a mixture of inorganic and organic layers. This means that the requirements for ion sputtering vary throughout the profile. The harder inorganic layers etch better with monatomic argon ions, but the organic P3HT PCBM layer sputters better with large argon cluster ions. Thermoscientific XPS systems can be configured with a monatomic and gas cluster ion source, or MAGSIS, that can do both, and so give the analyst a compositional depth profile of his novel mixed-layer devices. We saw in the previous slide how XPS can be used to measure compositional information. It can also be used to measure some electronic parameters relating to solar cell materials. If we collect photoelectrons with the highest possible kinetic energy, this allows us to investigate the valence electron orbitals in the sample. The energy at which the XPS spectrum begins, relative to the Fermi level, tells us the valence band offset. An example of a thin film of silicon nitride on silicon is shown on this slide, where the valence band offset was measured to be 1.4 electron volts. It's also possible to use XPS and related surface techniques to measure band gaps for some samples and to monitor how the band gap changes as a function of dopant concentration, for example. If we collect both the highest and lowest kinetic energy electrons, we can measure the work function of a sample. The highest energy electrons tell us something about the Fermi level and valence band, and the lowest energy electrons can tell us the work function. The example on this slide is for gold, where we measured the work function to be 5.1 eV. Since the measured work function is very sensitive to the condition of the surface, is there any carbon contamination, for example, it is often crucial to use argon gas clusters to clean the surface prior to measurement. In this example, we will see how XPS can be used to measure elemental and chemical composition information for the solar cell perovskite methyl ammonium lead iodide. The analyst needs to know this composition information because it can affect the performance of the solar cell device. Additionally, we can see how further XPS measurements can measure the valence band offset and ionization potential of the film. The first step of any XPS analysis is to acquire what we call a survey spectrum. This enables the analyst to identify all of the elements within the top 10 nanometers of the surface, even those which maybe shouldn't be there. The survey spectrum really allows the analyst to work out whether the sample is what they think it is. In this case, we can see the expected elements, including lead, nitrogen, and iodine. There is also a little bit of surface oxygen from exposing the sample to atmosphere. The intensity of the various peaks is proportional to the element, and we can then quantify those elements in the surface. In fact, XPS can quantify all elements except hydrogen and helium without having to use reference standard materials. As mentioned earlier, a key strength of XPS is the ability to acquire not only elemental information, but also chemical bonding state information. The survey spectrum showed that, as expected, there is carbon and nitrogen present in the surface of the sample. Higher energy resolution analysis of the carbon and nitrogen then give information regarding the chemical bonding states of these elements. The carbon is present in two bonding environments, as shown by the two peaks in the carbon spectrum. Carbon bonded to another carbon atom with a single bond, and carbon singly bonded to nitrogen. The nitrogen spectrum shows the presence of an N+ centered functional group. Having established the elemental and chemical composition of the sample surface, we can now move on to collect some electronic information. A valence band spectrum was acquired, and we can see that the leading edge of the spectrum is shifted from the Fermi level by 1.3 electron volts. The schematic shown with the spectrum illustrates how this information can then be incorporated into an energy level diagram. This kind of measurement can be extended to evaluate valence band offsets for one material in electrical contact with another, such as we might see in a solar cell device. We saw earlier with the gold example that XPS can be used to measure the work function of conducting materials. With semiconductors, such as methyl ammonium lead iodide, where there is no electron density at the Fermi level, we can measure the ionization potential of the sample. The ionization potential of the MAPI sample on this slide was measured as 5.6 electron volts, which is close to the cited literature value. Overall, for this perovskite sample, we have seen that XPS can provide a very comprehensive analysis. Solar cells based on CIGS thin films have demonstrated excellent efficiencies and offer a low cost potential as compared with bulk silicon-based solar cells, which are about 200 times thicker. CIGS solar cells consist of a thin film stack on a substrate, typically glass, as shown in the SEM image on the left-hand side of the slide. The molybdenum layer and the zinc oxide layer form the electrical contacts. The P-type 6 film acts as the sunlight absorber layer with a thin N-type cadmium sulfide layer forming a PN junction. The most common manufacturing methods are simultaneous or sequential evaporation or sputtering of copper, indium, and gallium. Vaporized selenium reacts with the metals in order to establish the final film composition. One of the major challenges in producing these thin film solar cells is to control the film composition. Reproducibility of the required layer design in commercial volumes has proven to be problematic. This is critical as the electrical properties of the solar cell depend on the exact composition of layers. A sample of a SIG solar cell was depth profiled using a thermoscientific XPS tool. Argonines were used to profile the sample. The depth scale was calibrated to a tantalum pentoxide standard. The calibration was checked using an SEM image of a cross-section of the sample. The sample was profiled using a rotating stage to get the best depth resolution through a very thick multi-layer sample. The sample rotation was performed off-axis, i.e. compucentrically, which enables several profiles to be carried out on the same sample. The depth profile on the left of the slide shows the structure of the solar cell. Firstly, we see the upper zinc oxide layer and the molybdenum substrate. A change in stoichiometry of the zinc oxide layer as a function of depth was observed. Quantitative chemical information like this can be important in identifying causes for failures, for example. The change in zinc to oxygen ratio may be a result of the interaction of the zinc oxide layer with the cadmium sulfide buffer layer, and this may affect the device performance. The depth profile shows clearly that there are composition gradients of gallium and indium in the SIG layer. These are likely to be a crucial factor in the performance of the device, influencing the band gap of the material. The XPS depth profile gives a standardless quantification of the SIG's film stack as a function of depth. A comparison of the XPS data with the Rutherford backscattering data from a similar test sample verifies the accuracy of that XPS quantification. In the case of the RBS, it was not possible to analyze a real product solar cell film, as was the case with the XPS example, but a similar test film deposited onto a wafer was examined. In both the XPS and RBS data, we can see the composition gradient of the gallium and indium in the SIG layer, where the two elements cross profiles close to 1.6 microns. Overall, we can see how good the quantification of the XPS technique is. We have seen in this presentation that XPS is a great technique for analyzing thin film solar cell materials. Parameters directly relating to device performance, such as elemental composition as a function of depth or valence band offset, can be measured. Thank you for listening to this presentation, and please feel free to email me at the address given at the bottom of the slide. I would now like to hand over to my colleague Simon, who will continue talking about new energy storage technologies using another technique available from Thermo Fisher Scientific.
Thank you, Paul, for the nice introduction. Welcome everyone to the second part of this webinar. And now we will focus on two other X-ray related techniques. One of them is X-ray diffraction, the other one is X-ray fluorescence spectroscopy. In this presentation, we will mainly focus on our benchtop instruments, one X-ray diffractometer and one energy dispersive X-ray fluorescence spectrometer, and how they are used for materials characterization. First, I will give a brief introduction into the principle of X-ray diffraction, which might not be familiar to everyone. Maybe you remember your physics class back during your school time. There is an experiment you do with a laser beam and a grating or slit. At this grating or slit, the light gets scattered, and there are constructive and destructive interferences which lead to peaks with minima and maxima. If we now reduce the size down to atoms, we will find a similar phenomena by also reducing the wavelengths down to X-rays. In a periodical 3D arrangement of atoms in a solid compound, the atoms form some planes, and these planes can act as a grating, and our X-rays get scattered at this grating, which also leads to a diffraction pattern similar to the one which is formed by the light. By then applying the fundamental formula of X-ray diffraction, which is called Bragg's law, we can calculate the lattice spacing, which is the distance between these planes. And these distances are very unique for different compounds. So on the bottom of this slide, you can see a mixture of different compounds which have different atomic planes, and all of these have different signals, which then can be used to identify the compounds in this mixture and even quantify them. Now we're coming to the real stars of this presentation, which are our two instruments. On the left side, you see the scientific ARL Quantix EDXOF instrument, which is an energy dispersive X-ray fluorescence spectrometer. We have direct excitation, and we use a primary beam filter. We have a rhodium or silver tube, and we use a silicon drift detector with a good energy resolution of 135 electron volts. The machine can measure under air, helium, or vacuum. On the right side, you see the semi-scientific ARL Equinox 100 X-ray diffractometer. This is a small benchtop instrument which uses a high brilliance, high flux microsource which is coupled to mirror optics for monochromization of the beam. It's available with a copper or a cobalt tube. We use a curved position sensitive detector, which I will explain later on. And several accessories are available for this instrument. The ARL Equinox product line uses a very sophisticated and unique principle of detection. We use a big band gas discharge type detector, which you can see on the right side of this slide. This enables us to have a completely static setup. So there is no movement, no motors involved. The sample is placed in the center of the radius of this detector, and then we shoot X-rays on our sample. These X-rays diffract and form these Debye cones, which you can see in the picture. These Debye cones then intersect with the detector and are detected, and therefore form the diffraction pattern, which can afterwards be analyzed. This detection has the big advantage that it happens in real time, covering up to 110 degrees to theta, which is the diffraction angle for our benchtop instruments. Now I want to show you some applications for these two methods, and I'm catching up with the CIGS solar cells Paul was showing in his presentation. Here's just a brief reminder of the stacking of this thin film solar cell material. So CIGS is the abbreviation for copper, indium, gallium selenide. It's a thin film solar cell, as I already mentioned. And there are two different types also available, cadmium telluride and amorphous silicon type solar cells. The big advantage of these type of materials is that it requires much less material but also exhibits a lower cell efficiency compared to crystalline solid solar cells like silicon. A typical CIGS stack is shown on the bottom of this slide. Usually you have a glass substrate and a molybdenum back electrode with less than 1 micrometer thickness. Then the CIGS absorber layer between 1 and 4 micrometers, followed by a cadmium sulfide buffer layer and a window consisting of zinc oxide and aluminum doped zinc oxide, which is the transparent front electrode. The combination of these two methods, X-ray diffraction and X-ray fluorescence spectroscopy, allows quality control of both the layer composition and the layer thicknesses of these type of thin film materials. And another advantage is that these two methods are non-destructive, so you can do the same analysis on the same sample. Now I'm going to give you some background information about how this analysis was carried out. So our sample is a CIGS solar cell pre-assembly, which consists of the molybdenum back electrode and the CIGS absorber layer. First, we did grazing incidence X-ray diffraction, which is a special technique for thin films. We used copper K-alpha radiation. The analysis time per diffraction pattern is 2 minutes. We carefully aligned our sample by using a omega Z stage to have control of the angle and the height of the sample. The data processing of the scans was done with Symphonix, which is the diffractometer control software, and MDI-J 2010. We also use PDF4+ database for the qualitative phase analysis. For EDXOF, the analysis parameters are shown in this table. So we used the palladium or copper primary beam filters. The atmosphere was air, and we used 2 different sets of conditions for different type of measured elements. So this is the result of our measurement with grazing incidence X-ray diffraction and different incidence angles. So the incidence angle between the beam and the sample was varied between 0.5 and 5 degrees omega in 0.5 degree steps. And by doing so, we can separate the layers from each other. So on the bottom, in blue, you can see the scan at 0.5 degrees. And then at 1.5 degrees, which is the red scan, you can see that there is an additional signal at around 40 degrees. So this is the second layer which appears. So therefore, we have some kind of depth profiling. If we now do phase analysis to see which peak belongs to which phase, we can clearly identify copper, gallium, indium selenide in the 1 degree scan, which is shown on the bottom. And at 5 degree, an additional peak appears, and this one belongs to molybdenum. So this one is the back electrode. So we can see the first layer at 1 degree, copper, indium, gallium selenide, the absorber layer, and by increasing the angle, we can also measure the deeper molybdenum layer, which is the back electrode. So maybe you ask yourself how X-ray fluorescence spectroscopy can help you in this case. But by using this technique, it's possible to quantify the layer thicknesses by using a fundamental parameter approach. Therefore, you have to do some calibration using bulk standards, and you have to know the composition of each layer, and you need one unique element in each layer. But if these conditions apply, you can get good precision on the layer thicknesses. Here you can see that for our CIGS layer we get 1.4 micrometer thickness, and for our molybdenum layer 0.34 micrometer, which is well in range of the specifications of this type of material. In this table you can see the repeatability of our EDXRF results, which are very good. These are different stacks of CIGS of different origins, and if you have a look on the sigma, so on the standard deviation, you can see that there's very little. So this the results are very repeatable, and so this technique is really very well suited for quality control of these types of material. As a conclusion of this talk, our benchtop EDXRF and XRD machines offer new possibilities for as well R&D and quality control labs, because they are very have a very small footprint, so they can even placed in the lab where the samples are made. The combination of EDXRF and XRD provides extra information when characterizing these materials, because you get very unique information of composition, thickness, and also the structural composition of your compounds. And depending on the application, these techniques are very complementary. So you get very complementary information. If you want to have more detailed information, we also have some application notes available on this topic. Last but not least, I want to emphasize that we also have other machines available, like wavelength dispersive, X-ray fluorescence spectrometers, even handhelds, and also a full portfolio of high-end floor-standing X-ray diffractometers beside the benchtops mentioned in this presentation. At the end, I hope you enjoyed the webinar, and I'd like to thank you for your attention. Feel free to reach out to me using the email address which is given in this slide. And if you want to have additional information, you can just follow the links which are also given on this slide. Thank you and goodbye.
Hello everyone, thank you very much for joining our session today. I would like to open the Q&A session by thanking our presenters for the insight that they just gave us into the topic of new energy storage technologies. And I would like to open a 10-minute Q&A session with the first question. I think this question is to Paul. What is the highest sample dimension that can fit to the XPS system?
Thank you for the question. So it depends on exactly which system you're looking at, but if we're talking about our newest system, the Nexa, then that can take quite large samples. So 60 millimeters by 60 millimeters in the X and Y dimension, and 20 millimeters thick. So 60 millimeters squared and 20 millimeters thick.
Great. Moving on to the next question. I think it's also for you, Paul. What is the difference between GDOES and XPS techniques regarding the chemical analysis of the surface?
Okay, so the GDOES is as far as I understand, I'm not an expert on this technique, is a glow discharge optical emission spectroscopy. And as far as I know, GDOS is very good at rapidly profiling through materials such as solar cell films, but as far as I know, it only gives you elemental composition information. Whereas, as he talked about in the presentation, one of the special features of XPS, perhaps its most special feature, is that it gives you chemical bonding state information. So if you see copper, is it bonded to another element? What is the oxidation state? It's that information which is extra for XPS compared to GDOS.
Great. The next question, I think that's for you, Raphael. What about the matrix effect when using XRF on thin films? sample with multi-thin layers?
Yes, thank you for the question. That is good, actually, yes. The software we'll use to process the data is going to take into account each of the matrix effect and the different absorption coefficient of the different elements in the different layers. And so, yes, matrix effect will occur, but the software is going to take into account each of those effects and using the fundamental parameters approach will still provide the correct results.
Great. And another question, are the instruments for 0 to 5 degree scan and above 5 degree scan different?
You mean that's on the XRD? That's on the XRD side?
Right.
Yeah, no, so the instrument is the same. We use a special sample support that can rotate, and so the angular range of that sample holder is approximately from 0 degree to about 30 or 40 degrees high. So we can use the same attachment to rotate with very high accuracy from 0 to 5 to 10 degrees, and the same attachment is used for both types of measurements. Yeah.
Clear. Another question, one of the listeners would be willing to know, what is the use of XRD in polymer characterization?
In polymer characterization, yes. So that
Exactly.
is totally different topic from thin films and they say this type of advanced material. But in the polymer industry, so you have different application with X-ray diffraction. One main side is you can identify the type of polymers you have. So if you have reference materials or unknown samples, you can perform the measurement and you can identify if you have polyethylene or a different type of polymers. But XRD will not provide any elemental information. It will only provide a rough idea of what the crystalline structure is or how much crystalline the material is. So you can also compute crystallinity or amorphous content of the polymer. And in a different type of setup, you can also evaluate the orientation of the material. So especially when polymers are extruded, then you can have orientation of the material. And then that orientation can also be evaluated by X-ray diffraction. But there are also different type of instruments that are used. There are small angle X-ray scatterings, and all of these falls in the umbrella of X-ray diffraction, but a slightly different type of instruments.
Clear. I have another question. It's about depth profiling. So the question is, can the ion etching affect the results of VB spectra during the depth profiling?
Okay, so thanks for the question. So VB, so that's going to be valence band spectra. So that's looking at the part of the XPS spectrum where we can pick up electronic information. I guess I'm not quite sure what you mean by changes, can it affect the results of valence band spectra? So two things I'll answer. One, of course, if you have a stack of films and you depth profile through the stack, then yes, of course, the valence band spectrum will change as you profile through different materials. And that can be very helpful. So, for example, if you had a layer of cadmium telluride on top of a layer of cadmium selenium telluride, then you could actually look at the valence band shift, and that will give you information about the electronic structure changing as you go through the films. If you mean, can the ion beam etching modify the valence band spectrum when perhaps you don't want it to, then yes, if you use an ion beam energy that is maybe too aggressive or too high, then that can modify the chemistry of the sample and then thereby modify the valence band spectrum. But in that case, it's usually possible to change the ion etching conditions to be a bit more gentle and try and find some conditions that don't adversely affect your valence band spectrum.
Thank you very much for your answer, Paul. Going to the next question, is it possible to analyze a cross-section of sample with multi-layers on micrometer's thickness?
Sorry, is that XPS, that one?
I believe so.
So So in terms of spatial, if you talk about cross-section, so if you have a multi-layer where you have micron layer thickness, you're generally better off with XPS using depth profiling. So sputter through the sample rather than cross-sectioning it and imaging it. If the layers are, tens of microns thick, then yes, you could do a cross-section. Or if they are thinner than that, if they may be around sort of, hundreds of nanometers or microns, then the other way that I have seen used is using a ultra-low angle microtomy, where you can do a very, very shallow cut across your stack, and then do imaging or line scans with XPS. But typically, I think you're better off doing depth profiling for that kind of range of thickness.
Great. The next question is about XRD analysis. So the question is there a single XRD instrument that do all the different types of XRD analysis and extract all the relevant information from it?
Yes. In a way, how can you make an instrument that performs every type of XRD measurement? That actually does not exist, because there are really different type of techniques. But when there are instruments from Thermo Fisher, and you have a broad range of instruments available that can cover a very broad range of applications. So you can do measurements on powders, on bulk material, on solids. You can do process control measurements like cement. You can do really very, very broad type of measurements. You can do dynamic studies. You can heat up your sample or cool it down. So there are very, very many type of analysis you can perform in a single instrument, but no single instrument can perform the absolute complete field of analysis possible in XRD. On the other hand, you will find no customer will actually need the complete range of measurement, because that would imply that they get samples from absolutely every possible type of materials, metals, coatings, plastics, polymers, pharmaceutical products. And basically no one has such a broad range of materials. So normally any type of lab, even an advanced lab in a university that has a broad range of samples, will still be able to cover all their samples with a single instrument. But you cannot find an instrument that really covers the absolute total range of X-ray diffraction. That does not really exist.
Right. And I think the last question, because our session is almost over, Paul, this question is for you. And the question is how to mitigate the effect of charging in UPS for non-conductive samples.
So UPS is a cousin technique of XPS. And instead of using X-rays, we use ultraviolet photons at around 21 eV compared to the 1,500 eV for XPS. So the best way of mitigating charging in UPS is to use a charge compensation source that you might have on our systems like the S-Lab or the Nexa. And we fire a beam of low-energy electrons and low-energy argonines at the surface. And as the photoelectrons come off under the effect of the photons, positive charge builds up, but the incoming low-energy electrons and argonines neutralize that charge. So with your UPS analysis for non-conductor samples, I would simply turn on the charge compensation source. And I think if you have an S-Lab system, the charge compensation mode you want to use is charge compensation electrostatic. If you use that mode, then you should be able to charge compensate your samples pretty well.
Clear. Paul, Raphael, thank you very much for the insights, and I'd like to thank our audience for all the great questions. I hope we answered some of them or most of them. We kindly invite you to visit our virtual booth or networking lounge in the meantime before the next session starts. And with that, I would like to close this session. Thank you very much for attending.
Thank you very much.